Yes, sir, it's coming.
So is it visible, sir?
Yes, visible, sir. That apple.
Okay.
Yeah.
Yes.
All the apples are there. Okay, sir.
So welcome all to the summer school on recent trend in speech processing and its application organized by KIT. And this is my presentation, Fusion of Information and Overview. So basically what we are doing here is, suppose we have a lot of information processing is done in any kind of digital signal processing things. So how we are basically fuse more than one information to a particular task. This is my work where we are able to generalize or able to get a fuse feature set to accomplish a particular task. So I will start from the very basic of information and gradually move on to my topic. So these are the introduction. In introduction, I will not discuss any mathematics, but simply I will try to give you then what is an information, which information is required for a particular task, as well as how much information we are going to process for a particular task. So since the information processing basically based on the task specific, that for a particular task, one information is very important, for other tasks it may not be so much important. So basically based on the task specific, we have to choose an information carefully such that we got the best performance. Now next we will discuss about the processing of information, fusion of information, a brief literature review such that we are able to know that what are the available fusion scheme and what is the limitation, and we will propose a particular fusion scheme that is my contribution in this particular slide or in this particular presentation, where we are developing a new technique through which we can process the information or process the features in a more innovative way or more optimum way to get a better performance. This is the work basically. So I will start. So I'll start with a Wikipedia introduction. That information is an abstract concept that refer to something which is the power to inform. So this is a standard textbook type of definition. But from my point of view, the information always represents something. Means information is anything which will give us some context of something. So information always represents something. So now I'll try to give you some information. Now first information is a speech signal. So in this speech signal, what this particular speech signal give us? So it may give us the speaker specific content, that this particular speech belongs to me or this particular speech belongs to Professor Das. Similarly, it may be belongs to someone for some particular age. Now second information it may give whether it is a male speech or female speech. This is another context, this is another information accompanied with this particular speech signal. Similarly, it may give us another information regarding the textual content, that what is the textual content of this particular speech. So I will highlighting three particular aspects of this particular speech signal. Means this type of information we can get from a particular single signal. So if a signal give us something or represent something or identify something, that is information. Now you go to the next beautiful apple. So this image give us what kind of information? The first information is what kind of fruit it is. It is an apple. This is one information. What is the color of the apple? That is another information. So what is the suppose the apple is good or bad? It may be also find out from the apple itself. So these are the another three important information we can find out the image of an apple. So for every signal we have different kind of application. Now we go to next signal. Third one is a three fingerprint. Now what are the information coming out from this three fingerprint? So we can see that whether this three fingerprint belongs to one person or not. This is one information. It maybe belongs to a male member or a female member if you are able to identify. This is second information. And normally fingerprints are fixed for a particular person. But when the person is become senior citizen or more than 70, the skin part is loosened up. So the fingerprint of a person in early 30s and late 70s may be different. So from that particular point of view, we can find out whether this is a adult fingerprint or a senior citizen fingerprint. This is another information. Now we came to the ECG signal. In this particular signal, we can find out that whether the particular patient from where this signal is captured is a healthy one or a faulty one. If the person is ill, how much? If the person is ill, what is the condition of his heart? All this information can be gathered from a particular signal. So whenever we are going to identify a task, then we have to very focus on what kind of information we are going to use. So we next the very important question, does a random signal carry information? We will discuss this in the later half of our presentation. We will give you such kind of question in interval such that all the participants can think, and we can also think that whether a random signal carry information. If it is carry information, what kind of information it will carry? What is there any information in the randomness or some other things? So we move to the next topic, which information. Now it is very important point that whenever we are going to find out a particular task, the information is important. Why it is important? Now we see. Now the first image is a colored image of an orange and apple. And second image is a black and white image. Now if our task is to separate out the apple and orange, then do you need the color information or the shape information? If our task is to separate out the orange and apple, then the shape is sufficient to identify which one is orange or which one is apple. Means if our task is to identify apple or orange, then the color information is not important. If we're going to process the color information, the computational time will be 3 times than the black and white processing, because color information contain RGB component and black and white is only content one information, 0 or 1, something like that. Now for identification of orange and apple, we don't need color information. That is why the information we have to choose is very important. Now we go to the next slide. There are 4 apples. Now if we want to find out each apple separately, then shape of the apple is almost similar. The color is little bit different. It is a very complicated task. Maybe nowadays it will be easy, but it may be theoretically a complicated task because size is almost similar. One red apple is there and another 3 apple is green apple is there. So to differentiate this green apple or differentiate these 4 apples, we need the shape information, shape of the apple, as well as we also need the color information. What we are going to say from this particular slide is that if we are going to find out a particular task to complete successfully, the information which we are going to use, the choosing information is very important. So in the first case, we are choosing only the shape information because the shapes are different. Now, if it is shape is same, then we have to take some other information also. Then only we are able to classify it. Now we go to the our part. Now the speech signal, because this is a speech-based workshop, the rest of the part will be discussed mainly on speech only. So now if this is a speech signal, it normally contains, all of you may know, all of you know that it will have 2 information. One is spectral information, one is LP residual information. Now in a particular task, suppose we are going to design a speaker recognition system in a clean environment. On a clean environment, the spectral information is enough to get a robust system, but get a very good system. But if the system works in a noisy environment, on that particular case, spectral information is performance of the spectral information is degraded. On that case, we are using LP residual information as a supplementary information to nullify the effect of noise. And using that LP residual information, the robustness of the system is improved. So based on the task, we have to choose the information very carefully. Now we move to the very important point, because you are all of you are a research scholar, so you may know all these things, but to get a idea about the topic, so we are trying to give you a very basic information regarding. Now this is a speech signal. Now we consider the length of the speech signal is 3 seconds, sampling frequency is 800 hertz. So we have 24,000 samples to process. Now, are you going to use all these samples, or we are going to use smaller number of samples? If it is going to the raw processing, then no problem. But if we are going to take smaller number of samples, then how much and how we pick the samples? What is the procedure? Same thing is applied here in case of this image also. Suppose the consider size of the image is 256 cos 256. So we have 65536 samples. We are going to process raw. If we are going to process it raw, no problem. If we have to modify it form, then we have to find out how. Now, instead of processing the raw information, if we modify the information in some way to get the desired output, this form is called Fisher extraction. Normally, in pattern recognition tasks, this is also a pattern recognition problem. In pattern recognition tasks, we are processing information in a modified form, not in the raw data. So this modification or of raw information is called Fisher extraction. And the compact form of the information is known as Fisher. So in the presentation, in this presentation, I will give you an idea of a new technique through which we can process the information in a more refined way to get a better performance. Now, in pattern recognition tasks, these Fisher sets are used to map different classes. Now, what are the classes? Classes means in a speaker recognition task, suppose 10 speakers are there. So we are going to model all these 10 speakers in 10 different sets. So all these sets, which is going to represent one speaker, is termed as a class. Similarly, in speaker recognition task, phoneme is a class. Class means a separate entity, uniquely differentiate from another one. Suppose if we are going in a speaker recognition task, we have 10 number of speaker, 1 to 10. So for one speaker, one model will be built. For second speaker, another model will be built. And these 10 models, then 10 different speakers will be called as a class in a pattern recognition problem. And as I already mentioned, that a Fisher extraction is a very crucial stage in any pattern recognition task. Now, I again put a question, is Fisher extraction still relevant? Because nowadays deep neural networks are coming in a very heavy way. It will changes all the course of research in the probabilistic domain. It will go on very rapidly to improve the performance of the system. So in some cases, in some DNN architecture, we don't even find out the Fisher also. If we give the structure, it will automatically capture the Fisher and do the training. Whatever is done here, it is done. But the Fisher extraction is still relevant. In which particular context the Fisher extraction is relevant, we will discuss in the discussion part after completing the presentation. You may also think in your direction that whether Fisher extraction is still relevant or not. And I am sure that it will be relevant, and it will be relevant for a very long time. What kind of technology is coming? Deep neural network, and after that, another technology is also coming. AI is also coming, some other technique will also coming, then also this feature extraction is still relevant in the near future. How we'll discuss in the later section, otherwise the discussion will be going another direction. Now, what is the need of an information fusion? As I have already mentioned you that in a particular context, one feature is sufficient. Now, there are some lines we are writing in this slide, but this is basically meaning is that for a particular task, in some cases, one feature is sufficient. Suppose the performance and robustness of a speech-based signal depends on the quality of the feature. I'm already told you, if you choose the perfect quality feature, then you are able to get a good perform system. Now, but in real time, the single feature may not be sufficient to address both performance and robustness issues simultaneously. As I have already told in the speaker recognition case, if the environment is non-clean, then normal spectral information or vocal track information is sufficient to design a system. But if there is some noise, on that case, the LP residual system, on that case, the spectral information based system is not sufficient to get the robustness. Robustness means how the system will be deal in the presence of noise. So on that case, we have to use more than one feature in a dignified way or in an optimum way to find out the response. So it is written here that in order to improve the performance and robustness, people suggest to use multiple features, more than one feature. And the technique of employed multiple features is termed as fusion technique. And this is where the base of this particular presentation is lying, that information fusion. Now we move to the next point, that the researcher reported various fusion techniques to improve the performance of the baseline system. But the performance of the system is not only depends upon the feature. It will definitely depends upon the feature, but this is not only the fact. How you are going to combine is also a very important point. There are different types of feature fusion technique. What kind of feature fusion technique you are going to use, that is very important to improve the performance. In the next few slides, you are able to understand the point. It because the available fusion scheme has certain demerits. Why it is? Because all the available fusion scheme have some problems. What kind of problems? We will discuss. Now, this issue that there are many fusion schemes and we need multiple information, but all this fusion scheme has different drawbacks. Suppose one feature fusion scheme have drawback X, then another will have Y. So for a generalized application, we cannot have a single fusion technique. So these things motivate us. So this is my PhD work. These things motivate us to give a look in the fusion technique which is available in the literature, and is there any possibility to improve, or is there anything, suppose there is a fusion X technique and fusion Y technique or fusion Z technique, can you develop any another technique by the combination of all these three techniques or all two techniques, such that we can able to nullify the disadvantage associated with this particular fusion technique. Now we move. Now we come to the technical part. Now this is a diagram of a speech-based recognition system. You may know all these things because Dr. Jagabandhu Mishra also give us and give you an idea about the speaker recognition tasks. Also, Dr. Madhusudan Singh also give you an idea about the replay detection system. We are also going to talk on that. Now we're taking a very simple speech-based recognition system. Now you see pre-processing is there, very important. Feature extraction, where the information is come to a compact form. Next, modeling. We can use probabilistic approach or discriminating approach or any kind of approach. KMF clustering, JMM, EVM, I vector, DNN technique. Next, we do the comparison and we got the result. Now, when we are going to fusion of information, then the fusion of information may be take place in 3 different directions. Now, the dotted line showing us that if the fusion is done in the fissure level, then it is called fissure level fusion. If the fusion is done in the model level, it is called model level fusion, or fusion is done in the score level, then it is called a score level fusion. Means in a pattern recognition problem, the fusion of information can be taking place in 3 different ways. In fissure level fusion, there may be n type of different techniques, but broadly, if the information is fused in the fissure level, then it is called fissure level fusion. So broadly, all this fusion scheme will be categorized into 3 different directions: fissure level, model level, and score level. We're going to discuss all these things in a detailed manner. Now, this is come to the fissure level fusion scheme. That is the definition. Fissure level fusion of multiple fissures for the purpose of building effective reference model is called fissure level fusion scheme. The basic concept is that if 2 fissures are fused, then it is called fissure level fusion scheme. This is the basic idea. Now, the previous diagram is modified in this way. Now, here we are using more than 1 fissure. Means we can use minimum 2 fissures, or we can use n number of fissures. Now, from suppose there is one signal is coming, pre-process with all the doing all the filtering, windowing to get the desired things. Then it will then from that particular signal, the fissure 1 is extracted. We got fissure 1, fissure 2 is extracted. Consider only 2 fissures. Now, after getting these 2 unique fissures, we are padding this fissure, we are concatenating this fissure to get the composite fissure set. Concatenation means like this. This is one fissure, this is another fissure. If we concatenate it like this, then this is a large fissure, the dimensions of the fissure will be increased. Now, after getting the composite fissure, rest of the process will be similar. We'll go for modeling, we'll go for comparison in the testing direction. But in the fissure level, we are using more than 1 fissures. Now, we came to the second topic. Okay, before that, we give you an idea about the work done where fissure level fusion scheme is applied. We are taking only few examples. First one is a speaker recognition task. Second one is a speaker identification and verification task. Fourth one is replay detection. Fifth one is phoneme recognition. Last one is speech recognition. Means fissure level fusion scheme is applied in almost all the fields: speaker recognition, replay detection, phoneme recognition, speech recognition, etc. So it is a widely used fusion scheme. Now we came to the second approach, model level fusion scheme. In this case, only 1 fissure is used, but we are using different model to find out the model specific parameters. Like suppose in model 1, we are modeling the fissure using GMM. In the second case, we are modeling the fissure with HMM. In the third case, we may modeling the fissure with DNN. And after getting all this model information, we are doing a composite model and doing the comparison. Means if the fissure is fused in the fissure level, it is called fissure level. If the information is fused in the model level, it is called model level fusion. This is the basic idea. Now, this is the 3 works we are showing you. This is speaker identification, speaker verification, and all these things. This model level fusion scheme is used very rarely, and we will discuss the reason in the later part. This model level fusion scheme is used very rarely, but this is a concept, so we are discussing these things. Now we came to the most important one and very easiest one, score level fusion scheme. In this case, you use multiple fissure, multiple model, whatever you want to do, you can do. But final thing is that Once the model is done, comparison is done, we get a score set. For model 1, we got a score set for model 2, or we got a score set for model 3. So after getting all this result, we are doing the fusion. Means we are doing the fusion in the score level and get a decision. That is why this is called score level fusion scheme. Score level fusion scheme can be classified into two types. First one is you use single feature multiple modeling techniques. Like this, you use single feature multiple modeling techniques, but the composite model here, composite model will be not built. I will show you in the next slide. And second one is multiple feature are accepted, multiple features are used using single model or multiple model. Means in one case single feature, multiple model. Second case multiple feature, single model or multiple model. These are the two classifications. Now we move to the diagram. This is very important. Now you see, this is the first case, feature score level fusion scheme in one where we are using only one feature extraction technique. Now feature is extracted. We have n number of model. It may be 2, it may be 100, whatever it is the task specific. Now model 1, doing the modeling, do the comparison, get a score. Get a score through here. Now in the second case, model 2 also come, do the comparison, we got a score. Similarly, model n will process in the same direction and go, we got a score. So all these three scores are combined and get a resultant score. We will give you the output. Now, in the second direction, you see, you can have n number of features and we can have n numbers of model. Now, in case of modeling case, this n may be 1. On that case, you have multiple features, one model, and you have multiple features, multiple model. Means x1, x2, xn can be different model or the same model. And similarly, do the comparison, getting the result. Second case, doing the comparison, getting the result. And third case, doing the comparison and getting the result. After getting all this result, we will do some linear weighted summation or some other technique, product rule. There are 7 types of different rules are there, how to find out the resultant score, but the most weighted linear weighted sum is the mostly used, and we got the output. Now in this particular case, what is our benefit? Benefit, it is very simple. You design 2 feature, single model, get the score, combine it and get the result. This is the most simplistic and most easiest. That is why it is used in very widely. Now you see the list. This is very few things which is relevant. I will put in here, but you may find thousands of work in score level fusion scheme. Very easy, but there are various very important drawbacks is there in the score level fusion scheme also. So that is why after doing a proper literature survey, we are able to find out that all these technique have different problems. Now we are going to discuss the problems such that you have a better idea that whether we need another combination scheme or another fusion scheme. Now, limitation of feature level fusion scheme. Before that, I can show you the slide. Okay. Yes. Now you see, second case MFCC plus phase information. Third case MFCC plus pH feature. Fourth case, fifth case MFCC plus sonority feature. LPCC plus LP residual feature. Means in all these cases, one feature is large, one feature is small. This is the drawback here. I'll show you or I will discuss it. Now in feature level combination scheme, if the combined feature, if the individual feature have large dimension. Suppose one feature has 39 dimension, another feature has 39 dimension. Now, if we concatenated these two features, then the resultant dimension will be 78. Now, if you have a 78 dimensional feature, then the curse of dimensionality came into picture. What is this means? It is already proven that if the feature length is increasing, suppose first we are using 30, we got some performance X. Next we get 50 feature length, we got performance Y. Suppose Y is greater than X, means Y has the superior. If you go on increasing, the performance Y will be decreasing. It means that the feature level, the length of the feature will be increased up to a particular length. After that, the performance will be degraded, and this is called curse of dimensionality. It is basically due to the redundancy. If we increase the feature length, the redundancy increases. So due to the increase in the redundancy, the performance of the system will be reduced. That is why the feature level fusion scheme is only applicable to smaller dimension feature. Means one 30 dimension, another 5 dimension. So resultant feature will be 35 dimension. In that case, it will be work very fine. But in normal our speech processing tasks, we use MFCC. It will standard, it will be 39 dimension, 13, 13, 13. And in the noisy case, we are using LP residual information, which is also having 39 dimension. So if we concatenated in the feature level, it becomes 78. So curse of dimensionality came into picture. In this particular case, the performance will be not increasing, it will going to decrease. The baseline performance will be decreased using the fuse information or using multiple information. So this is the first drawback of the feature level fusion scheme. Now we came to the model level fusion scheme. It is in comparison with feature level, it is more difficult. What is the difficulty? Suppose there is a model GMM. It will represent mean, variance, and weight. A GMM model can be represented with these three parameters: mean vector, covariance matrix, and weight of the Gaussians. Okay. Now in the DNN case, it will not the case. We are not able to get mean, variance, and weight. It will give some biasing, or it will give some normalization or some other parameter. Now, if the model is different, the matching of this parameter to get a composite model is very difficult. This is the reason why this model level fusion scheme is very rarely used. But this is one particular aspect of the fusion, so we are going to discuss it here, or we are discussing right now. But model level, the main drawback of the model level, as I already mentioned, that the find out the composite model from different parameter of different modeling scheme is a tedious and very difficult job. We have to do lots of mapping. Some cases the mappings are not correct. That is why this model level fusion scheme is not applicable. Now we move to the third one. This is very widely used. As I have already mentioned, it is very simple. First drawback. Whenever we are finding out the resultant score after all the calculation, we need the weight of the system. Weight means, suppose there is a system X. The performance of the system will be 90%. There is another system whose performance is 80%. There is another system whose performance is 95%. So all these three systems, there are different performance. So whenever we are getting the resultant, whenever we are going to find out the resultant score, we have to give more weight to the higher performing system. Suppose for 95%, we will give more weight than the 70% performance based system. That is why in real time scenario, it is very difficult to find out the actual weight of a particular system. If this weighting factor is somehow mismatched, the performance will be degraded. First case. Second case, in score level fusion, the resultant score, the resultant performance will be improved only when the features are highly complementary in nature. Suppose there is a feature X, it will represent something. Another feature Y, it will represent some other thing. Means if the information represented by X and Y are complementary, means there is no redundancy or very less redundancy or base overlapping is there, then only score level fusion scheme will perform in a better way. Third one is, suppose there is a speaker recognition system. We have 100 users. We do all this feature level, we do all this score level fusion scheme. Now suppose we want to increase the number of users. Suppose normally you take in a college, suppose we have 100 students. We do a student attendance system. Now suppose due to some reason in class 10, after 10 days, we have another 10 students. Now this induction of this 10 students, it takes very long time, because one student coming, two student coming, we all this training, we do all the calculation to get the perfect weight again. That is why induction of a new user is a time consuming process in score level fusion scheme. So these are the drawbacks. Now, based on whenever we are finding all these drawbacks, then we can think in a little bit different way, that in fusion scheme, feature level fusion, the main problem is the increase in the length, because we are doing the feature level in this way, concatenation. Then we think that instead of concatenation, can you do like a padding like this? Means this is one feature, this is another feature, do a padding. So in this case, what is the advantage? The curse of dimensionality case will not come in, because the dimension of the feature will be not increasing. First thing. Second thing, we think that can we do a model level fusion such that matching of this parameter will be not there. So we can use a model level fusion where the matching will be not there. So we will going to these things in detail. Now we go to the next step, the proposed fusion scheme. Whatever I am telling you, this is right there. So no need to go it again. Okay, 1 point. Now our fusion scheme will be working in the probabilistic classifier. Why we are choosing probabilistic classifier? Because before DNN, all the speech-based application will be based on probabilistic classifier. GMM, GMM, UVM, I vector, GMM, HMM, all are probabilistic approach. So we are designing the system for probabilistic approach only, because whatever the DNN is coming into picture, DNN definitely have some serious drawbacks. So we'll discuss in the discussion part what are the drawbacks of the DNN, because we are going to find we are going to also discuss the recent trend in this particular direction. And we have chosen probabilistic approach because it is widely used in various speech-based applications. Now we move on to our proposed scheme, where we can effectively use the fusion principle. Now this is little bit mathematics. Generally, a GMM model can be represented by mean vector mu, variance vector sigma, and omega is the weight vector. Okay. Now D represent the dimension of the feature vector, M is the Gaussian mixture size. Now in practical GMM based system, full covariance matrix is replaced by diagonal element. You already know if you are working in GMM. So practical GMM system can be collectively represented by the equation number 2. Means the complicated sigma become a two-dimensional sigma. So now based on this equation number 2, we are designing a very suitable system which is effectively used in the fusion technique. Now you see, now this is the diagram. block diagrammatic approach. I am going to give you a very detailed idea about this. Now, suppose there is a speech signal. First one is training phase. You all of you know what is training and testing. The speech signal. First, we consider there is a feature XTR and another feature YTR. Now, all this going in a some separate direction. Now, first we extract this feature and doing the modeling. Modeling means mu x, sigma x, and omega x. Similarly, using feature y, we design another model, mu y, sigma y, omega y. Okay? And now do the composite modeling. Now, how we are doing the composite modeling? I already told you that we are using the padding scheme instead of concatenation. And I will show you in a mathematical way also. Now, the composite model will be stored. Now, training process is over. Now, in the testing phase, whenever a signal is coming, this is feature XTR, same technique we are using. Feature YTX, same technique we are using. And we are doing a composite feature. That composite feature is also using the padding process, not the concatenation, such that the dimension of the feature will be not increased. Now, after this, the comparison will be taking place between the composite feature set as well as the composite model. Now, after the comparison, if it is an identification task, the speaker is identified. If it is a verification task, the speaker will be accept and reject. Okay, this is the basic idea. Now, how the composite model are formed? Here is the main contribution of our work is that how we are going to do the composite is very simple. We are simply tweaking a particular things and getting a very good result. But in the tweaking that instead of concatenation, can we do padding? And by removing the curse of dimensionality issue. Now we move to the mathematical representation. See, this is mu x, mu y. This is simply padding, and we got the mu z, sigma z, wz. And here it is multiplied with half because the summation of all the weight vectors or of the weight parameter will be 1. To make it 1 to the standard JMM principle, we make divided by half to get such that the summation of all the component in wz, omega z will be 1. Now, in the testing scenario, the testing feature ZTX is also formed using the padding process. Means simply changing the concatenation domain to padding domain, we are changing the course of the fusion scheme. Now, these are the presentation mu x, mu z, the mean vector. This is I have already told you. Let me move to the next point. Now, example. For example point of view, I am showing you. This is mu x. The dimension will be 256 cos 39. As I have already mentioned, the feature length is 39. 256 is the Gaussian size. Now, this is mu y. Now, the resultant mu that you see, number of rows will be increasing, but the number of column will be remain same as 39. That is why the dimension of this particular system is not increasing. So the cause of dimensionality issue is not coming, and we are also getting the benefit of multiple features by removing the main drawback of the feature level fusion scheme. Again, since we are comparison will be taking place simultaneously of both these features, that is why the weighting factor, which is the most difficult part in the score level combination scheme or score level fusion scheme, is also eliminated. Means we are eliminating the first drawback of model level feature level fusion scheme. We are also eliminating the drawback of the score level fusion scheme, and we are also eliminating the drawback of the model level fusion scheme because we are using the same modeling technique. We are not using any different modeling technique. We are using the same modeling technique, but we are doing the fusion in the model level. This is our small contribution in this particular work, which will give us a very good result. We will discuss in the discuss in the second half of our presentation. Now we have the fusion. GMM UVM is also similar. You know that only difference is that first speakers are adopted with the corresponding UVM independently, then we padding it. Now it is almost similar. And we are only keep it accept and reject because GMM UVM are only used in speaker verification task, normally not used in speaker identification. So here only difference is that UVM is used to model the adopt the speaker models. That is why there is simple difference. There is no other big difference. Now we came to the I vector based system. Why we need I vector based system? The GMM UVM based SB system suffers in adverse condition like channel session variation. Means suppose if you are training the system with microphone data, or if you are going to test the system with channel data, the performance will be degraded. Session variation means suppose today we are discussing something, or today we are recording, and after suppose 6 months, 1 month, 2 months, we are give our data, there will be definitely a variation because we are a human speaking system cannot produce the same sentence or same thing twice. We are not a machine, so there will be definitely some difference. If the session is varied in a summer, if you're recording something, it may be different than the winter, because in winter there may be some throat problem, something is there. In summer, not, this kind of things will be not there. So session and channel variation create lot of trouble in the GMM UVM based system. That drawbacks can be eliminated using I vector based system. So I'll show you the proposed I vector based system. Now this is the I vector based system. This is very standard definition. We are only tweaking is the thing is that instead of one feature, we are using multiple feature. Now, in the train case, feature XTR and YTR coming. We find out the sufficient statistics or Bohm-Swell statistics. Whoever working in the I vector case, they know what is Bohm-Swell statistics or sufficient statistics. We are specifically telling here. Find out for XTR and also find out for YTR. And in this case, we are using EFM to find out the sufficient statistics. Then we find out the combined statistics using these two. And this is the mathematical representation we are given here. Next, we are using total variability matrix to find out the I vector. Using the compensation technique to find out compensation technique, which is LDA and WCCN, to channel and session variation, using cosine kernel distancing and decision by thresholding technique to find out the result. Here the main difference is that instead of using number of Gaussian in different rows, we are making a super vector. Super vector means if we have two features like this, this is GMM1, this is GMM2. So this is GMM, number of mixer, two mixer. And when it becomes super vector, it becomes like this. That is why the mathematical parameter of combination will be given like this in this direction. But here the concatenation is not done in the feature level. Concatenation done in the model level. That is why the cause of dimensionality problem is not coming here, though we are doing the concatenation. This is the beauty of I vector. That is why till 2016, 17, 18, I vector is the standard technique, state-of-the-art technique in the speaker verification field. Now this is the example how we are doing the I vector based comparison. This is 356 cos 1024. NY is 356 cos 1024, and finally the NZ becomes 356 cos 2048. Now this 356 is the number of speaker model and 2048 is the super vector using the concatenation of the GMM model. This is the I vector based system. Now till this we are discussing GMM, GMM UVM and I vector based system. These three systems are used in speaker identification, speaker verification, limited data speaker verification, replay detection, etc. But because speech processing also is a very speech recognition also a very big field in the speech processing domain. So we are also design our system for GMM HMM based system such that we can use the multiple information in speech recognition domain also. So GMM HMM is widely used before DNN. Now speech recognition is only done in DNN, but there are a lot of drawback as I already mentioned. We'll discuss. Now a complete GMM HMM system can be modeled using two parameters M and N and three probabilities measure A, B, and Z. N is the number of HMM state. M is the Gaussian mixture size to represent the state observation. A is the state transition probability. Transition probability means from one state to another state. B is the observation probability, and pi represent the initial state distribution. Those who are working in GMM, HMM or speech recognition, they may know in detail about this particular point. Now this is the proposed scheme for GMM UVM based system. Now this is Fisher XTR YTR, same modeling, same AX BX pi X, AY BY pi Y, and composite model is also built in some same way, and composite Fisher set is doing it, and finally we have got the recognized sentence using the multiple information. Here is only one difference is there. In speaker recognition, suppose one text file is coming. We know that that particular text file will be coming from the same person. So whenever we are doing the comparison for all the speech frame, we do the comparison and average it and get the result. But in speaker recognition, in speech recognition, this is not the case. In speech recognition, for each frame, for speech frame, we have one result. Means suppose in a text file, if we have 1000 frames, we have 1000 results. So that is why there is a little bit tweaking in the testing process. We will showing it here. Step transition probability is a square matrix, so it will be and the row of equal to 1 summation of all the rows. So we are multiplying with half to make the step transition probability of row is equal to 1. And GMM HMM based ASR system, the observation probability is given by GMM system. So same technique we are using to find out the composite observation probability BZ. Now fusion of initial step transition matrix pi. Pi is independent of Fisher, means pi is deriving from the speech transcription which we are presenting here. Speech transcription means suppose there is a speech file coming. So from 1 second to 3 seconds, what is the phoneme is present? From 3 seconds to 10 seconds, what are the phonemes is present? All the information will be given in a file. Which who working in the speech recognition case, they know. From this speech transcription, we are finding out the initial state distribution. So whatever the Fisher you are using, it will not change. So pi z will be means the composite initial state distribution will be same as pi x and pi y. Now we came to the testing part. In the testing part, for each Fisher vector, we are designing one. We are getting one result. Now, since we are using composite Fisher set, so suppose in the first case for Fisher X we have 100 frames, for Fisher Y we have 100 frames. So if we make a padding operation, then we have 200 frames, means 200 result. So what we are doing it, we are doing it in this way. Suppose this is Fisher 1. I am trying to show it through my hand such that you can able to understand. Suppose these four fingers are Fisher 1 frames. These four fingers are Fisher 2 frames. Fisher 2 frames. Now we are padding in such a way that frame 1 of Fisher 1 and frame 1 of Fisher 2 will be in like this direction. Means first we came Fisher frame 1 of Fisher 1, next frame 1 of Fisher 2, frame 2 of Fisher 1, frame 2 of Fisher 2, means one after another we are doing the matching the Fisher vector, and we are making the system in such a way that for 2 Fisher vector we will get one decision, and for 200 space frame we will get 100 decision, as we have to get 100 decision only. This way, from this particular mathematical representation, the concept will be clear that first frame 1, 2 and 1.1, second frame is 1.2 to 2.5. Now in the second case, second Fisher, it is 3.3 to 3.3 and it's 6.6 to 6.6, such that we can able to understand how it is making. Now in the composite Fisher set, 1.2, 1.1, 3.3, 3.2, 1.2, 2.5, 6.6, 6.2, means one after another. Now these first two, 1.2 to 3.2, give one decision, means 2 frame, 1 decision, 2 frame, 1 decision. Using that technique, we are able to reduce the number of decisions such that the number of decision will be equal to the individual system. This way, we are doing the fusion in the GMM HMM domain. What is the time? It is 11. In the domain. So here, okay, here we are here we are trying to give you an idea, or trying to do the Fisher level, trying to do the fusion of information in a different way, and the result of this will be very encouraging. I'll show in my second lecture. Since this is a theory, we are putting it, we propose some scheme, so we have to verify whether this scheme is theoretically good or practically good. So we have demonstrated this new scheme in different applications: speaker identification, speaker verification, limited data speaker verification, replay detection, as well as speech recognition. So I'll give a very briefly the idea about all these things. This is a speaker identification task. Already all of you know. Only here is the identified speaker. It is a 1 to n comparison. Means if some speaker is coming, suppose there are 100 speaker models are there. So the incoming test speech signal will be compared with 100 speakers to get the result. So it is a 1 is to n comparison. But in the speaker verification case, it is 1 to 1, because in speaker verification, the speaker is already claiming that I am X. So it will only compare with X and find out whether it is actually X or some imposter. So this is little bit easier than speaker recognition, speaker identification with respect to the computational cost. Now, limited data speaker verification is a specific case of speaker verification where the training and testing data is limited. Normally, we are considering a scenario where training data is enough, but testing data is limited to 10 seconds. And as you have already know that the performance of the system is always depends upon the quality of data and quantity of data. That is why if we have sufficient number of data, the performance will be good. And this is the challenge in the limited data speaker recognition is that speaker verification is that we don't have sufficient data. So whenever there is no large amount of data is present, on that case, how the system will be performed. That is the implication of the, or that is the challenge in the limited data speaker verification. Now, in the next slide, I am showing the same diagram Dr. Madhusudan Singh showed yesterday. I have also present on that particular discussion. He is basically working in the replay detection, in doing a fabulous work on that particular dimension. I have also a part from that particular replay attack detection case. Now you can see this is the target speaker, actual speech. It will directly go to the speaker verification system, accept and reject. But whenever the target speaker speech is stolen or recorded by someone else, and used as the target speaker, then the system should identify that this is not a original speaker voice. It is a replayed voice. That is the concept of replay attack detection. So here we have to only find whether the incoming signal is the original signal or replay signal. And rest of the part will be done by the speaker verification system. We don't bother about the speaker verification in this case. In this case, our main aim is to find out whether the signal is coming from a speaker recognition original speaker or a imposter or a replayed speech. And this is the standard block diagram of a speech recognition. Feature extraction, there is two models. One is acoustic model. Acoustic model means whatever the training samples are coming, that based on that training samples, we are doing the acoustic model. This model will be nothing but the representation of different phoning of that particular language. Now, the language model, what is it represented? Suppose in a particular language, there are some rules. What kind of rules? Suppose I am a boy. It cannot be I are a boy. So this is the rule that after I, it should be am, not are, not something else. That is why these rules, from that particular rules, we are having language model. And in the matching domain, there are two types of domain. In the testing case also, suppose some speech frames are coming, it will showing that this speech frame is X1, X2, X3, X4. Now, in the matching domain, symbolic domain, what we are doing is that we are finding out the probability whether after this particular frame it will be X1 or X2 or X3 or X4. Based on that probability, we will assign the phoneme to next to the first frame. And similarly, the process will be going on and we are getting the recognized sentence output. Okay, these are the 5 specific work we are going to discuss using our proposed fusion scheme in the second set of our lecture. Speaker identification, speaker verification, limited data speaker verification, replay attack detection, as well as speaker recognition. I hope I will not bore you, but this is the first presentation where we are discussing regarding the fusion of information in a pattern recognition domain. And we will try to give you an idea of a new scheme where we will try to eliminate the drawback. So now discussion, we can do some little bit of discussion in these 2 questions. And also if you have any question regarding this, I'll try to answer it. If you are unable to answer from my side, I'll definitely give it the answer in the later half of this presentation or some other day. Thank you very much for your patient listening. Thank you, sir, for giving me this opportunity. So if you have any question, you can ask, or I will start with the discussion with this particular 2 question. Sir. Chetta, sir. Hello.
Hello, sir.
Hello.
Yes. Yes, sir. Sir,
हाँ
I'm finished here.
हाँ sir, बोलिए.
No, I'm finished here, sir. If you have any query or anyone have any query,
Sibsagar,
so
sir, we have one hands-on session after this. I think for this one.
No, sir. We have
some case studies. Some case studies there.
Case study means I will going to discuss the representation of all these feature set in different direction. Okay, speaker identification, speaker verification, and various other direction. 5 different application we have done. So we will give in detail description on that case. So if you don't have any question, I may think that you get bored by this presentation,
No,
but
sir.
uh, uh,
Actually, I
uh,
was out for the 20 minutes because
no,
official.
no, sir, I'm not telling about, I'm not telling about you. I am telling about the other
Not that.
participant.
Yeah,
But this is
Sibsagar?
very important.
Yes, sir. I want to ask something.
Yes.
Yes, tell me, sir.
Hello, am I audible?
Yes,
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 Anu.
yes.
Yes, sir. My question is, in the last presentation of Madhusudan sir also, and in various cases, we use the combination of different feature vectors. So that is come under this fusion scheme or not? I mean, that's not. I mean,
Yes,
in that
definitely.
case, sir used the MFCC and LP residual signal, or in if I say about that South in the last there was a presentation on shouted speech detection. There here we have used that DCT IC DCT IPLER and MFCC features combined. So this is all come under the fusion scheme, correct?
All come under the fusion scheme, and particularly I don't know about the other case, but in Madhusudan sir case, he is using Bossari's toolkit. That is a score level, one kind of score level fusion scheme. Yes, Deep Shankar, it is a fusion scheme, and that is a score level fusion scheme. If you go in detail in the, tell me.
Yes, sir. And the other question is the model selection which we are using. So here we are using the Gaussian mixture model, and we have used the GMM, UBM, GMM, HMM fusion model. And so the thing is, so here we have to choose a model in such a way that the parameters are correlated. I mean, we can't choose a deep neural network and GMM, and so that wouldn't be very helpful, correct? Yes.
Because our approach is only for probabilistic case. And there is a constraint that we have to use. Here, our main objective is to use the different feature, not different model. So that is why we are keeping one model but different feature. The main difference in the existing one and our one is that we are not doing model level fusion, but we are doing the fusion in the model level. You getting my point?
Yes, sir. So we are collecting different features, passing it to a model, and after that we are combining the results.
Yes, combining the results. And in that, it is done in the training section, but in the testing section, we are doing the feature level combination, doing the padding scheme, and we got a fabulous result. I will show you the results.
Sir, can you move back to that ASR part? I mean, where you have used that language model thing.
Yes, this one.
So this is also true for the when we do ASR using CALD. They are also we train a language model, and also the acoustic model training is there.
Thing. Because since in the CALD or any other toolkit, everything is written there. We are just going to using some command. That is why we are not able to go in detail whatever is there in the system. But if you are doing a coding using GMM or GMM HMM by MATLAB, in MATLAB, then you are able to understand each line that this is done, we are doing it, we are extracting the parameter, we are using this, we are using GMM model here, this is the language model, like this. This is the standard diagram. Wherever you are using CALD or some other toolkit, they will follow this model. The procedure are only different. Rest of the things are same.
Okay.
Krishna sir.
Yes, sir.
Actually, can we this segmenting all the bird noise, like the bird sounds? Because why I'm telling, we can use some existing data set in Australia, in New Zealand, so many data sets are available for the bird sounds. So I have kept around 120 birds at my home, okay, for last, I think, from 2006. Okay,
Very
so
good, sir.
14 to 15 varieties of birds are there. So I want to do some work because I can collect the data, miss getting or not. Miss, so how we can do start, we'll discuss in details, okay? Because lots of sounds are coming, and that I can also collect the data, and data sets are available. So how you can segment the sounds of the bird, or or the nature of the bird, what birds want now. Suppose say they are very hungry, so what type of sound is there? Or they want
Definitely.
to mate. Okay, what type of sound is there? Or okay, so like that means I want to do some work and I can collect the data also, because that is all the
Definitely.
works are with me for the last 2
Definitely,
years.
it will be a very interesting work. But we have to, from my perspective, my point of view, we have to take one particular task at a time.
Yes, yes, yes.
Suppose if you going to recognize which bird species is
Yes,
that,
yes, yeah, yeah.
that will be different. And if you're going to find out what are the mood of the bird, it is hungry or some fear is there, then that will be another study. So
Okay.
taking one task at a
I
time,
don't know,
then
means
it will
we'll
be
start from somewhere. We'll start from somewhere, and what are the equipments of required to collect the speech data or sound? Okay, their sounds. We'll also see that one. We'll discuss in detail. Okay, some 30 minutes, 40
yes,
minutes
yes,
discussion will be there. So I am
yes,
very much
definitely, it can be
interested
done.
to come do that kind of work one at least, because they are with
Definitely,
me
sir.
for
It
the
will be
last more than 15 years or 16, 17,
yes,
18 years.
yes, yes,
And they
yes.
are laying eggs and
Mm.
their families now growing up and getting into.
Yes, correct, sir. Correct. Okay,
Okay, sir.
so
Any other questions for this one?
Yes, sir. There is another question from Anthony Paul. How does information fusion handle conflicting or inconsistent data from different sources?
I actually once again, madam.
Yes, Mona Lisa. Ask again. Hello, Mona Lisa. Ask the question again. Hello. Mona Lisa, unmute yourself and I'll repeat the question again. I think some network issue or somewhere. Bala, any question?
Extracting the data from a particular source. We are discussing here is, suppose we have a data, not a feature. We have a data. Suppose we have a speech signal, and that from that particular speech signal we are extracting the data. We are not extracting the data from a source. Suppose now I am speaking. Suppose in some cases I may speak very fluently. This is a sufficient data you are considering. Suppose due to some reason I am unable to speak fluently. That is insufficient or inconsistent data. So on that case, there may be some other approach. But here, see, if we have a data, then how we are expecting the different information is of extracting from that particular source is our concern in this particular case. So if I am getting your question correctly, that if we have a data, then only we can find out the feature. If the data is not adequate, or if the data is not sufficient, then also we are able to find out some data in case of your limited data speaker verification case. But if the data is inconsistent, or if the data is not available at all on that case, so it will be a very difficult task to extract the information from that case. Is it okay?
Mona Lisa, is it okay?
Yes, sir. Yes, sir. Thank you, sir.
Okay. Okay, if you don't have any other question, we have two questions to discuss. One is, does a random signal carry information? So if anyone want to comment on this particular case.
Yes, anyone?
Random signal means what? Periodic signal or any signal?
No, random signal is not periodic. Random signal means any signal which is random. Means suppose we are generating one signal now, after 1 second we are unable to generate the same signal. That is random. So is random signal carry information?
Yes, sir. I think so. Like it may have some sort of information, might not be like relevant to us, but I think carries signal, like information.
Okay. So okay. Tell me, Deepsankar.
Yes, so I also think that random signal carry information because the unvoiced sounds which are produced through our mouth, that signals, that things are not periodic. They are completely random. But they carry the sounds like sa, the and sa sound. So I think yeah, that they don't have any periodicity, but they do carry information.
So from my point of view, that periodicity is not linked to randomness. Randomness is you cannot able to find out. If a signal is aperiodic, you can able to find out what is the signal is, but it is aperiodic. That is not random. Random means you are unable to determine. But now I will give you one example. The random signal always carry information, but we are unable to extract the information, or we don't have any proper technique to find out what kind of information it will carry. But one example I can give you. There is a spread spectrum modulation technique in communication. All of you know about this? Spread spectrum modulation, where the PN sequence is generated, pseudo random noise sequences is generated. Okay, so you may not get it, but the random signal carry information, that is for sure.
Krishna sir, just this year I came across one news that trees can talk each other. That Japanese scientist has discovered. I don't know whether they are like that random signal through that one is they're communicating something, some information is going on, which is not.
The problem is like that only. Suppose all of you are from the speech processing domain. You know that MFCC is doing fabulous, but the LP residual is not part of this information. But LP residual also contain information, but we don't know how to find out the information correctly. That is the case. Everything carry information, but the processing of that information, the technique we don't know. Now that become very important. Is Fisher extraction is still relevant? How many of you think that it is relevant? In what context? You can guess the answer also, no problem. Because we are here, because I am telling it is a discussion. I am not going to judge you or anything, but you can just say that Fisher extraction is relevant or not, because I am talking 1 hour and again going to discuss another half an hour, 1.5 hours on this topic only.
Yes, exactly.
But we know that because
answer.
Yes, sir. So nowadays, many self-supervised models are there where we don't need to extract the features. It is on automatically creating the features from the speech signal itself. But speech extraction is still relevant because to understand the emotions or to find out the tonal quality, we do not need features, the prosodic features. So I think speech extraction is still relevant in that case.
This is not only okay. This is a good point.
Yes, Babatunde, sir, another person raising his hand. Yes, Babatunde, you just give.
Okay, thank you, sir. I still believe feature extraction is very relevant. The reason being that so when you're dealing with maybe periodic signal like that, still have to like extract the kinds of features that we use for training. So it depends on the types of signal it is. Let's say this random signal like that. So it is very important to see how you extract the best features that we used for training like that. So feature extraction is very relevant from my own end. Thank you.
Anyone else, Bala?
Anyone else?
You can also add, Bala.
Yeah, it's very important, sir, particularly in data analysis and signal processing, because it helps in terms of dimensional reductions and also improving model performances, and also it helps in integrating the model in the real world application. So it's very important.
Sir, I also want to add one thing.
Yes.
So that prosodic feature aside, the feature extraction is still very relevant also because if you put the raw data and create the features by self-supervised model, so the thing is that we need a huge computational power. So yeah, by extracting features, we are compressing the information in such a way that we can implement it in low computational environment as well. So in that case, feature extraction is still needed, because yeah, the
Yes.
feature is very good in collecting information and compressing the raw information.
Yes. So my point here it is, nowadays DNN techniques are coming into place. So you just give them the idea that this number of features, this number of filter, this number of coefficient we require, it will automatically generate the feature and do the processing. But except DNN, in any other cases, we need feature extraction, because nowadays you see the main drawback of the DNN is that it needs a very huge amount of data to build their system. If the data is less, it will not work. You may not believe that if the data is small, the performance of DNN will be lesser than the GMM system only. If GMM, we have 1 hour of data, GMM will performance will be 60%. If you use that 1 hour of data in DNN, it will give you 30-40%. But if data will be 100 hours, DNN will give 90%, and GMM cannot get 90%. It will start in 70, 75 or something like that. But suppose nowadays the research is going in various directions. I give you one example. The replay detection task will broadly start in 2015. I think you remember Madhusudan sir already told you yesterday. It is starting in 2015. Now, whenever a new dimension of research is going on that case, we don't have sufficient amount of data to train a DNN system. On that case, we definitely need the feature engineering prospect of a particular signal or particular technique or particular area to deal with the information first. Now, in India, nowadays, you are not going to find out any improvement in English speech recognition, because already it is done by Google, Facebook, almost 99% type of performance they are getting, because they are training 6 lakhs hours of data. But suppose we India have lot of languages. Suppose we have one language called Bodo language. Can we get a 6 lakhs hours of data in that case? But if you're going to research on Bodo language, the DNN framework will be not working. Nowadays, another speaker diarization field is going. Language diarization field is going. Jagabandhu's your second speaker, Jagabandhu Mishra, is doing on language diarization or speaker diarization field. This is very new field. You don't have enough amount of data, or you may not be able to get enough amount of data to deal with the DNN prospect. So whenever a new field is emerging, on that case, feature engineering definitely taking place. Now it is DNN. Next time it will come something else. But whatever it is coming, it will data hungry. There is only one particular process which is a probabilistic approach, where we only have freedom to work with less amount of data. And if data is less, feature extraction, feature engineering will be definitely there to improve the performance. So feature extraction, feature engineering still relevant, will relevant in the near future, because in most of the part of the research community, we don't have sufficient amount of data or resources to do our work. So with this line, I conclude my talk for now. So we'll assemble at 12 o'clock for the next presentation. Hope, I don't know you are enjoying or not, but in the second part, you'll definitely get enjoyment. If you know something about, if you are working in this particular fields, you will get lot of information from the case study part, where I'll practically show you different tasks using our proposed fusion scheme. What are the experiments we have done, how we have done various experiments, how to check, how the fisher is selected, what are the information we have to carry when we are trying to find out the fisher. We'll see you on 12 o'clock. Okay, thank you. Thank you, sir.
Thank you, sir. Sir, we'll meet another after 30 minutes for another session.
Yes, sir. We will meet on 12 o'clock, sir.
Yes, sir.
Thank you very much, sir.
Okay, sir.
Okay, sir.
Thank you, sir.
Okay.
So the session is end here. We can meet at after 30 minutes. Thank you very much.